will share my...
Everyone, 1 minute, excuse me, sir, 1 minute.
Okay, sure.
One minute. Good afternoon, everyone. I welcome the speaker and all the participants to the remaining half of the second technical session. Today, for this session, we have three speakers. Rishikesh Chakraborty, Dr. Rishikesh Chakraborty sir from Jorhat Engineering College.
Ma'am?
Yes?
Ma'am, we have two speakers. One is Rishikesh Chakraborty from Jorhat Engineering College. Another
Yes.
one is Kesbi.
Oh, okay, sorry. I think there are three speakers for today. Sorry. Okay, two speakers, as Rajiv Bordolo informed me. Dr. Rishikesh Chakraborty sir from Jorhat Engineering College and Professor Rakesh Bait sir from Jammu University. And Dr. Siddhananda Sharma sir and Professor Rakesh Bait sir, both of them were the speakers of yesterday's first technical session, and now we have only two. Okay, so hope the session will be very interesting and interactive too. So over to Rajiv Bordole. You can proceed. Rajiv, you can proceed now.
Okay. So you told everything. So I request Dr. Chakraborty sir to deliver his speech.
Okay. You can hear me, right?
Okay. You're audible.
Yes. So I will share my screen, and please don't call me sir. I'm really young. Okay. So can you see my screen?
Yeah. Yeah.
Okay. So yes, as I don't know if you know about the plan of this session. So what I am going to talk about is these errors in measurement, errors in experiments. Okay, and before I start, let me introduce myself. I am Rishikesh Chakraborty from Jorhat Engineering College. I recently joined JEC as a assistant professor. And another disclaimer before I begin is that I'm not an experimental physicist. I do not do experiments. I have a PhD in theoretical physics. So these things I just learned when I was in college, when I was studying my master's and my bachelor's at Tezpur University. And these things still help me. So even now, I actually work on testing gravity theories, general relativity theories with experiments. So there are some experiments which are testing gravity theories. They have some data. So those data, I compare those data with the predictions of my theories. So the things that I learned in college, they still help me. Okay, but I'm not really experienced with the recent development in experimental physics. This is just about errors, accuracy, precision, and a little bit of data analysis that I think would be helpful for students. Okay, and anyway, so before I begin, I would like to thank the organizers to give me this opportunity to speak. Okay, so let's begin. First, this is my outline of the talk. Okay, so the basic thing, the most important thing is to understand this picture in the right hand side. So there is some random plot. You can see there is a curve here and some data points with some error bars. So our basic idea is to understand what is this thing. Okay, and motivation. So first I will talk about motivation. Why should we bother about errors, accuracy, data analysis, all these things. I'll give you some idea about accuracy, precision, which are related to the experiments that you perform. Definition of error also. Then importance of this error in experiments. Okay, and how do these errors propagate? So this error tend to get bigger as you have some formulas. So in those formulas, these errors, they become bigger. Okay, and then finally some statistical analysis, least square fitting, simple straight line fitting method I will show you, and I will also give you some examples of how to relate whatever I teach you today, this to the actual lab setting, in the actual lab setting. And finally, I will give you where you can learn more, some more books and everything. Okay, so let's begin. Okay, so motivation, why bother? Why should we care about errors? So there is a saying in Assamese that "Manu matre bhul hoy." Okay, men are prone to making mistakes. So we will always make mistakes. So we'll make mistakes in doing the experiment also. That's why there will always be some error in the experiment. Okay, and we have seen from experience that no measurements, however carefully made, can be completely free of uncertainties or errors. Okay, so this uncertainty and error, it is inevitable. So I can give you one example. Right now, at this moment, the most precise instrument on Earth, one of the most precise experiment on Earth is the gravitational wave detector. It's called. It has different names. The ones in the US are called LIGO, and one in the Europe is called Virgo. ESO Virgo. So they are very precise measuring instrument because it's very hard to measure gravitational waves. So basically, it is a Michaelson interferometer. Those people who are in physics, they would know that Michaelson interferometer. It has two arms, L-shaped. It's very big, 4 kilometer long, and this arms where you actually measure the changes in some distance, it is underground. Okay, to avoid uncertainties, to minimize uncertainties, and it is very sophisticated. Actually, those arms are vacuum, and the mirror they have it's almost kept at 0 Kelvin, almost 0 Kelvin. So it's very sophisticated instrument, but it still has some error associated with it, the measurements. But it is very less. Right now, I think it is less than 10 to the power minus 22. That means if you measure 1 meter, then the error may be 10 to the power minus 22. It's less than 10 to the power minus 22 meter. So even in those kind of very sophisticated instruments, there is always an error. So errors are inevitable. So for the first part, we will learn these errors and uncertainties, how to define them, and can we minimize them? Spoiler alert, yes, we can minimize them, but we cannot completely get rid of them, all right? And we will learn how to propagate, how these errors propagate. We will learn to calculate them, actually, and statistical analysis. So the definition, so the error, it's not like the error in your normal sense. In your daily life, you make some mistake, you call it error. But in science, it like the word error, it doesn't carry the usual connotations of the term mistake or blunder. Okay, so error in scientific measurement means the inevitable uncertainty, okay, that attends all measurements. Okay, so errors in science are not mistakes, okay? And so they cannot be eliminated. Okay? We cannot eliminate them by being careful. We can only minimize them. So error can be minimized but not completely eliminated. All right, and these error calculations, they give us an idea of how much trustable our result is. Okay, if our result is actually correct or not. Suppose you are doing some experiment, you found some result, but you did not calculate the error, then nobody will trust your results as these calculations are very important. Okay. So here in this talk, I would use this word error and uncertainty interchangeably. So they mean basically the same thing, error and uncertainty. Okay, so first let us check what is the error here in this experiment. So a lot of you have the students actually you have done this experiment of measuring the acceleration due to gravity on Earth by using a simple pendulum. Right. So this is a diagram. Here is your string. The length of the string is L, and there is a bob of mass M. So what you do is you change the length of the string and you calculate the time period. Okay, then you square the time period, plot it, and then you can calculate the acceleration due to gravity. Okay, and you know the theoretical value is 9.8 meter per second square that you find in your books. Okay, but when you did the experiment, suppose you measured 9.7 meter per second square, right? So you know your actual value, what should be the answer, you know it, right? 9.8 meter per second. So you can calculate, maybe you have calculated this relative error, so which is just 9.7 minus 9.8 divided by 9.7. That gives you like minus 0.01, right? It's a relative error, it's a dimension-based number. Okay, so this method gives you error only when you know your theoretical value. In most cases, you do not know that. And this error, this relative error, you do not know where it came from. It may be coming from your measurement in length or your measurement in time. Okay, so you do not know where it is coming from, so you wouldn't know how to minimize this error. So we would like to have some other idea of error. Okay. So that's why we have to take a step back and understand what is accuracy and what is precision. Okay, precision and accuracy. So I think you have learned this in your higher secondary classes, accuracy and precision. The first chapter in class 11, I think. Okay, so accuracy. So first, the accuracy of a measurement system is the degree of closeness of the measurement of a quantity to its true value. Right? So suppose you know your actual value of the measurement. This is the theoretical value. And this is your measured value here. So accuracy is the notion of how close your measured value to the actual value. Okay. And what is precision? Precision is precision of a measurement system, also called reproducibility, is the degree to which repeated measurements under unchanged condition show the same result. So precision is given by this spread in this normal distribution. Okay, so if your measurement is more precise, then this length of this line will be smaller. Okay, if your calculations are more precise. Okay, if your calculations are more accurate, then this accuracy line will be shorter. Right? So this is the definition of accuracy and precision. So basically in actually real experiments where we do not know what we are measuring, the value of what we are measuring, talking about accuracy there is meaningless, because we cannot have the accuracy there because we do not know the reference value, right? But you can talk about precision. All right. Next, let's see how to write error with the answer. Okay. So suppose you're measuring your weight. You're standing on this weighing machine, digital weighing machine. There it shows that the weight is 84.7. So it only gives us data up to one digit after the decimal. Okay, and the least count here is 0.1 kg. Okay, so the error or the uncertainty will be half of this least count. That's why we are writing it as 84.7 plus minus 0.05 kg. Alright, so the maximum that this person can weigh is 84.75 kg, because the maximum, for the maximum you have to consider this positive sign here, and the minimum you consider this negative sign, you get 84.65 kg. So the person's weight according to this weighing machine is between 84.65 to 84.75. So it is a more meaningful way rather than saying just 84.7 kg. All right. Similarly, suppose you are measuring a distance. As example, I have the measurement of a pencil here. So this is your pencil. Suppose you are measuring the pencil with a scale or a ruler. Okay, and you get it as 36 millimeters. Okay, and we know the least count for this scale is 1 mm, and least count is 1 mm means the uncertainty will be 0.05. Okay, 0.5 mm. Okay, so least count is 1 mm, so the uncertainty will be 0.5 mm. That's why the probable range for the length of this scale, this pencil is from 35.5 to 36.5 mm. So you can write it as L equal to 36.0 plus minus 0.5 mm. Okay. Similarly, in case of digital devices, this is a digital device, reading of a voltmeter. So here, if it is properly calibrated and everything, then the uncertainty of measuring the voltage here will be half of the least count. So least count is 0.01 volt, so uncertainty would be 0.005 volt. So you can represent it like this. So this quantity on the right is called the best estimate, and plus minus this quantity is called the uncertainty. Okay, so you know now what is error and what is the best estimate. Best estimate is the answer, the result you get, and the uncertainty is given by this quantity after the plus minus sign. So why should we care about the uncertainty? The importance of uncertainty. It is because it's really important. I will show you how. Okay. So suppose somebody gave you a crown, okay, or a crown or a ring of, but you don't know what material. Okay, it may be gold or it may be some alloy. All right, and you can measure the density of this material. Okay, you have some instrument and you can measure the density of the instrument. Okay, so I gave this ring to two guys, one George and Martha. Okay, so George's instrument is not very good. So his error bars, his uncertainty error is huge. It's a big uncertainty. But Martha's instrument is good. Uncertainty is less. Okay, and we know that the density of gold is 15.5 gram per centimeter cube, and density of alloy is 13.8 gram per centimeter cube. Now, George and Martha has to calculate the density of the ring so that they can verify if it is actually gold or some alloy. So, both of them, they calculated. For George, the best estimate is 15, suppose. Okay, 15 here. This is his data point, 15. And since his instrument is not very good and he made some mistakes in measurement, so his error bars is huge. His uncertainty is big. So his probable range is from 13.5 to 16.5 gram per centimeter cube. And Martha's, according to Martha's measurement, she got her best estimate is 13.9. Okay, and the probable range is from 13.7 to 14.1. So now you can see, according to George's measurement, this density of gold and alloy both come under his probable range. So he cannot tell if the ring is actually gold or alloy. But Martha can tell because gold is totally excluded from her range. Okay, that's why it's good to have proper uncertainty, a smaller uncertainty in your measurements. Okay, that's about your importance of uncertainty. So now we know that there are uncertainties in experiments. So we would like to know from where these uncertainties come. Okay, so there are two types of error or uncertainties. The first is called the systematic error. Okay, and example is if a clock is running consistently 5% late, so it is hard to detect. So you are doing some experiment. Suppose you are calculating the curve. This not actually curve there. You cannot. Suppose you are doing some experiment, okay, and you are measuring the time, and your clock is always showing a 5% late time. Okay, so that is very hard. That would be very hard to detect. So if you do not know, if you do not have another clock, then it would be hard to detect that you actually have this error. Okay, and this error of this type affect all the measurements the same way. Okay, and it can be a result of your faulty calibration, okay, on the part of observer. All right. Other kind of error is your random error. Okay, random error. So this is just fluctuation in observation. Okay. And these errors can be reduced only by repeated measurements. So reproducing them is essentially one of improving experimental method and refining technique. So if you do a lot of measurements, then only you can reduce your random error in your experiment. So if you do infinite times the measurement, then your random error will be zero. Okay. So these are two types of experimental errors that you can have. So we can see these two errors in some image, some plot. Not plot, actually, schematic diagram. Okay. So see here, we have some measurements. So these dots are actually measured, our data points, measured values. Okay. And the result, the actual result is supposed somewhere here at the center. And these circles, they give us some reference of how accurate or how accurate and how precise our results are. Okay. So in this experiment, we can say the random error is small and systematic error is also small. Why? Because you can see all these results, okay, in this experiment, they are lying close. So that means random error is small. And they are also lying close to the actual value. So we can say systematic error is also small. But if they are lying close, but all of these points are shifted by some distance from the actual value, in that case, we can say that there is some systematic error because all of these measurements are affected by some kind of error in the instrument. Similarly, in this third picture, you can see here, all these points, data points, are spread apart. That means random error is large here, but systematic error is small because they are evenly distributed. And in the last figure, in this fourth figure, you can say the random error is large because they are spread apart, and systematic error is also large because they are shifted towards the right. Okay. So this is a pictorial representation of random error and systematic error. We can also see this in this kind of graphs. So you can see here, we have this x-axis and y-axis, we have plotted some data. And this orange line is the actual result. But this blue line is our measured value. So for every measurement of x, our y is shifted by some amount. So we can say this is precise, this measurement is precise, here this is precise, but it has systematic error because all the measurements are shifted by some amount. You can see. All right. What about this picture, this graph? Here, it is precise because our error bars are very small. But again, it has random error and also systematic error, some sort of. How about this? This one, we can say this is accurate. This plot is accurate because you can see here in the plot and you can have an idea. It is accurate, but it doesn't have systematic error. The errors are only random error. And accurate because everything is lying, this actual value is actually lying within all the error bars. So we can say this to be an accurate measurement. Yeah, I think you have some idea now what is accuracy, what is precision, and you can relate to it using these pictorial representations. So up to now, do you have any questions, students? If you have any questions, you can stop me anytime and ask me. Okay, just let me know. So if there is no question, we can proceed maybe. So as I told you, this is the way to represent the result of an experiment. First, you have to write the best estimate, and then you have to write the uncertainty. And now we will talk about how to add these errors and how to subtract errors, how to multiply, how to divide errors. Okay. So actually what happens in experiments, you suppose, I will go back to your simple pendulum experiment again. There you measure time period, right? Time period and length. And those measurements will have some uncertainties associated with them, as I will show you later in a more in a better way actually. So I will show you that. And the measurement of time period and length will have some uncertainties associated with them. So how would those uncertainties will be converted to the uncertainty in acceleration due to gravity? Okay, that we need to know. Okay, that's why we have to learn how these errors are added, how they are subtracted, how they are multiplied, and how they are divided. Okay. So result of a measurement is expressed in this form. So best estimate, which is called the P best, plus minus uncertainty, which is delta P. Okay. So suppose we have these masses of these two blocks. Okay, weight of P, this block is suppose 31.10 plus minus 0.05 kg. Okay. The weight of this Q, this block is 31.30 plus minus 0.05 kg. All right. So if you want the total weight, the sum of this weight of this P and Q, then you have to add those, and you just simply you can add them. So 31.10 plus minus 0.05 kg plus 31.30 plus minus 0.05 kg. Okay. So now what can we do? Let's see what can we do. So we know this for measurement of P, weight can be represented like this: P best plus minus delta P. And for measurement of Q, it can be represented as Q best plus minus delta P. So for the best estimate, we just add P best and Q best. So best estimate of P plus Q is P best plus Q best. Okay. So highest probable value here can be P best plus Q best plus the sum of these two errors. And the lowest we can have is again the sum of these two errors, but with a negative sign, minus. Okay, so we can just write it as P best plus Q best plus minus delta P plus delta Q. Okay, so similarly it is same for differences also. So the uncertainty in difference P minus Q is also the sum delta P plus delta Q of the original uncertainties. Okay. Now we can talk about something called fractional or relative uncertainty. So what is fractional or relative uncertainty? It is the uncertainty divided by the best estimate. Okay, suppose your uncertainty is delta X and your best estimate is X best. We'll just take the ratio. Just divide uncertainty by the best estimate. Actually, the mod of the best estimate. Absolute value of the best estimate. For example, if you measure a length and that is your answer is suppose 50 and plus minus 1 cm, where 1 cm is the uncertainty. In that case, your fractional or relative uncertainty would be delta L by L best. So delta L is 1 cm and L best is 50 cm. So it gives you 0.02, and it's a dimensionless number. So what is the importance of this fractional or relative uncertainty? It tells you how much trustable your results are. Okay, suppose you are measuring, suppose you are measuring length, okay, and your uncertainty is suppose 1 kilometer, okay, and your best estimate is 10 kilometer. So your relative uncertainty is something like 10%. But suppose you are measuring your uncertainty for a short distance. Suppose your best estimate is now suppose 2 kilometer and uncertainty is 1 kilometer. So in that case, your relative uncertainty is 50%. So that is not a good measurement. So calculating this fractional or relative uncertainty tells you how accurate your, how good your value is actually. So fractional uncertainty is an approximate indication of the quality of measurement. So whatever the size of quantity measured. You can measure 10 kilometers also, you can measure 1 kilometer also. So if the error associated with 1 kilometer is 1 kilometer, then your measurement is not very good because it's only error, so 100% error you have. in that case. Okay. So now, what about the propagation of errors in product and ratio? So here we learned in difference and sum. Here let's talk about product and ratio for some relative uncertainty. So that would be given by your delta x by y. Suppose we are considering a ratio and the best estimate is x by y. Okay, so we can write it as this. So x by y, we can write it as this, right? X best, x is x best plus delta x, the best estimate plus uncertainty, and for y, the best estimate, again, the uncertainty. So from this numerator and denominator both, you take x best and y best common. So they will come out and you will be able to write like this: 1 plus minus delta x by x best divided by 1 plus minus delta y by y best. Okay. So from this equation, okay, x by y, from this equation, what can be the maximum value? The maximum value will be when the numerator has a positive sign and the denominator has a negative sign. That would be the maximum value. So I'm writing here x best divided by y best times 1 plus delta x by x best divided by 1 minus delta y by y best. So then you can expand this. You can do a binomial expansion. Just keep 1 plus delta x by x best like this. This is your 1 minus delta y by y best to the power minus 1. And if you take a binomial expansion, it becomes plus, since you have a minus 1 in the exponent. Take the product of 1 minus delta x by x best and 1 plus delta y by y best, you will get this quantity. Plus some order where you have delta x, delta y, square term, which will be extremely small. So you make like that. So similarly, you can also find the minimum value it can have. So that would be when your numerator has negative sign and denominator has positive sign. So similarly, you do binomial expansion and you will find this result, right? So from these two equations, you can find this delta x by delta y and delta x by y divided by x by y. So that would be your delta x by x best plus delta y by y best. Okay. So about this addition, subtraction, all this product and division rule. So there is just two simple rules. So when your measured quantities are added or subtracted, errors add. Okay, you have to add the errors. And when the measured quantities are multiplied or divided, the relative errors add. Okay, relative errors add, not the absolute errors. Okay. So now there is a question. So can we improve our estimation of this uncertainty? Okay. Can we improve this estimation? So the answer is yes. So how can we do that? So in general, when you are measuring these uncertainties in addition, suppose, so that would be your delta P plus delta Q. So actually it may be overestimated. Why? Because this may happen if we underestimate, if we have underestimated P by full amount delta P and Q by full amount delta Q. Okay. So actually, usually it's not always if your quantities that you are measuring are independent. Okay. So that's why I am saying here that if P and Q are independently measured, we only have 50% chance that an underestimate in X is accompanied by an overestimate in Y or vice versa. So this is a very unlikely event. So actually it has a proof considering some distribution functions. If you are interested, you can look at the book. I will give you the reference of the book at the end of this talk. You can have a look. But right now we can skip that proof, and what is the take-home message now is that to avoid this overestimation, we can add the uncertainties in quadrature. Okay, so uncertainties are added in quadrature to avoid overestimation. So this gives us a very simple and nice usable formula. Okay. So this also takes us to the propagation of errors. Okay. Suppose you are measuring some quantity q, which is the sum of x plus y. Okay, x you have measurement for x, and y also you have measurement for y. So you have to calculate q. So the uncertainty would be now like this. Added in quadrature means this guy. You have a square root. Then under the square root, you have the uncertainty squared and sum. Because sum of the uncertainty squared and then taken a square root. So that is called added in quadrature. So this quantity will always be smaller than delta x plus delta y, which we got earlier. Okay. Suppose this is a bit more general case here, q, where q is the sum of x, y up to z, and then there are some divisions also, u to u, from u to up to w. Okay, so in that case also, the errors are added in quadrature. To find delta q, you have to square the uncertainties, then add them, and then take a square. It will all again be smaller than this whole sum. Okay. So here is an example. So suppose your one length measurement is 5.3 plus minus 0.2 cm, and another is L2, which is 7.2 plus minus 0.2 cm. Okay. So if you add these two, so suppose L, the sum of these two lengths is L1 plus L2, and imagine that these measurements are independent. Okay. So delta L would be this delta L1 squared is 0.2 cm squared plus delta L2 squared. So I missed the 2 here. So delta L2 squared. So you square them, add them, and they can take a square root, you will get 3 mm. So it is a smaller number than 4 mm, which you would have gotten if you had used the previous formula, delta L1 plus delta L2. So that will give you 4 mm. But here you will have 3 mm. All right. For two quantities, it doesn't matter much, but if you are measuring large number of quantities and measurables, the difference is like 1 over square root of n. So it makes a difference when you have a lot of data points. Okay. So again, we can extend this rule for product or quotient. Okay. So suppose you're measuring q. Okay, that can be calculated from x, product of x to up to z, divided by product of u to up to w. Okay. So in that case, you can find this relative uncertainty. It is given by this whole quantity, the square root delta x by x square plus up to delta z by z square plus delta u by u square plus up to delta w by w square. So this will also be smaller than this number, this expression. Similarly, here also the relative errors for n measurables are the same, and we gain 1 over square root n relative error. Okay. So finally, you can go to a general formula, a very general formula. Suppose this is your formula in the expression in your experiment. I will give you an example. Maybe then you will understand it better. So this is your formula where your function depends on this xi plus 1, all these quantities. Okay. And provided all errors associated with xi plus 1 to up to xn, they are independent and random. Okay. Then you can calculate the uncertainties associated with q using this formula. Sorry, this formula where delta q is square root the partial derivative of this q with respect to xi, then delta xi multiplied by delta xi square plus up to xn. So you take the partial derivative of q with respect to all these variables, and multiply that with uncertainties associated with the variable, square it, add it, then take a square root, and this will give you this delta q, okay, associated with this q, uncertainty in q. So this is an example for this kind of formula, q equal to x to the power n. The fractional uncertainty is delta q by Q equal to N times delta X by X. Okay. All right. So any questions till now? No questions. I think everyone is sleeping. Anyway, so let's continue towards the formula. An example here. I'm again coming back to this experiment of calculating acceleration due to gravity using a simple pendulum. So there you measure length of the wire or the string and the time period or oscillation period. And this is the formula that you use, G equal to 4 pi square L over T square. Okay, for this case, you can calculate this error associated with delta G. Suppose you have some error associated with L when you measure the length of the string. Your ruler will have some least count. Okay, suppose it is 1 mm. So the error associated with the measurement of your length will be 0.5 mm. Okay, so delta L will be 0.5 mm. It's delta L. Similarly, you are measuring the time using stopwatch, and the least count of the stopwatch would be 1 second maybe. And so if it is 1 second, then the error associated with the time measurement will be 0.5 seconds. So delta T would be 0.5 seconds. So you would know these two quantities, delta L and delta T. So you can find this delta G by delta L by taking partial derivative of this quantity with respect to L. So this gives you 4 pi square times 1 over T square. Okay. Similarly, you need this quantity delta G by del T, del G by del T. So this is given by taking partial derivative of G with respect to T. You have this minus 4 pi square L over T cube. All right. So a bit more detailed here. I also have some numbers for you. Here I'm calculating the relative uncertainty. I'm going from a different route, not exactly from this route, delta G, but from a different route. So let's see what is del T by T. So del T by T you can find by this equation, taking this equation, delta of T square by T square. So this gives you 2 delta T by T. Okay. And delta L by L, same because there is no square there. So you find the relative uncertainty in delta G. So delta G by G will be equal to square root this guy in L, this guy in T. Okay. So suppose this is your L measurement, 92.95 plus minus 0.1 cm. This is your time period measurement. Okay. So your best estimate, you can put everything in this formula, or formula for G, except for this uncertainties in L and T. You put everything here. This gives you 979 centimeter per second. Okay, second square. Okay. And from this equation, L equal to 92.95 plus minus 0.1 cm, you can find the relative uncertainty in measuring this quantity. So that would be 0.1 divided by 92.95. So it is approximately up to 0.1%. Similarly for here also, it is approximately up to 0.2%. All right. So relative uncertainty in G in terms of percentage is 0.1 square plus 2 times 0.2 square. So it's 0.4%. Now we just multiply this G both sides. That will give you delta G, which is just 4 cm per second square. So your actual value, 980 centimeter per second square, actually lies between 479 plus minus 4 cm per second square. That's how it is important, and that's how you practically do estimate your error. Okay. Now we again come to this plot of systematic and random errors. So you already saw this plot, right? Here you have some reference lines, so you can tell how much is your systematic error here, how much is your random error. But what if you do not know? If you do not know about the actual value, if you do not know the actual value, then what will happen? You cannot know if there is actually systematic error in the system or not. If you do not know the reference lines here, then you do not know what is the actual value. So then you cannot tell that what is your systematic error. So this happens in real experiments. Right? Suppose you are doing a very cutting edge experiment and you do not know the value of the thing you're measuring. Okay? In that case, it would be very hard to know about the systematic errors. So what you can do is do the experiment very carefully, error all systematic errors by being very careful, and then analyze the random errors. Okay. So to do that, we take help of some quantities called standard deviation. Sorry. So let's see one example now. So suppose you are measuring some quantity and you have 5 measurements, 5 values, 71, 72, 72, 73, and 71. Okay. And then you can calculate your best estimate, and that would be your mean. You take the mean of all this quantity, and your mean will be 71.8. Okay. This is your formula for mean. You can, when you have the mean, you can calculate the deviation from the mean of your measured value. And your deviation would be, for the first case, that is 71.71 minus 71.8. So that is your deviation. That would be minus 0.8. So similarly, for all measurements, you can calculate the deviation. Okay. But deviation is not really a good quantity to analyze random errors. You square it, because when you only consider the deviation, the sum of all deviation is 0. That's why you square it. Squaring it gives you a non-zero value. So sum of all this di squared is 2.8. 2.8 is sum of di squared. Okay. So these linear deviations, they are not good because the sum of all those deviations is 0. Have 0 average. So that's why we go squares. We calculate this d square, sum of d square. That's called the standard deviation. Sum of this d square. And actually the proper definition is square root 1 over n times the sum of di square. This gives you the standard deviation. So standard deviation also gives you the uncertainty with an experiment, associated with an experiment. And this formula has an improved form. If you want, you can have a look at that. So actually this coefficient here is not actually 1 over n. It's actually 1 over n minus 1. There is a crucial reason behind this. So if you want to know, you can read the book and find out. It's very interesting. So I will encourage you to read about standard deviation. So why this coefficient is not 1 over n actually, and why it is 1 over n minus 1. Okay. So standard deviation is also called root mean square deviation. Okay. So finally, before going to the analysis, I have this some rules for you. Significant digits, you can just have a look at them and then carry on. I think you already know about significant digits. Okay. So this first rule is experimental errors should be always rounded to one significant digit. So you only need to have one significant digit. So this first one, this is wrong because we have like a lot of digits here. You just need to get rid of this 3, 8, and 5. So the right is 9.82 plus minus 0.2. So this is, so everything I have told you till now, it is actually the good practice done in all experiments. Even if you go to very good labs later for PhDs and everything, and you have to follow this kind of rules. Otherwise, if you write your paper, if you do some experiments, your results will not be accepted by the community. Okay. There is an exception of this result. This is if the leading significant digit is of the leading significant digit of the error is 1, then you have to keep one more digit. Yes. This is an example for Everest. 8,848 plus minus 1.5 meter high. Second rule, so last significant figure in the answer should be the same order of magnitude as the uncertainty. So these are some examples: 92.8 plus minus 0.3, 92 plus minus 3, 90, 30. Okay. So this is an advice. During the calculation, retain one more digit than is finally required, just so that your calculations become easier. Okay. So any questions till now? Students, you can still hear me, right? Did I lose you?
Yes, you're.
Okay.
You can proceed.
Yes. So this is the last part. Data analysis. I will give you a simple definition, just an idea actually. So suppose you are doing some experiment. Suppose you are doing the experiment on calculating acceleration due to gravity by using simple pendulum. In that case, you have to draw a plot, right? So in your x-axis there will be t square and y-axis there will be L. Okay. So if you draw this plot, your points will be like randomly distributed on the plane, 2D plane. Okay. They will not be exactly on a straight line. If it is exactly on a straight line, then you have made some blunder in your calculations, in your measurements. So what people used to do, what we used to do when I was in higher secondary classes, so we just measure everything, and if one point is not on the straight line, we change that measurement and bring that point over the straight line. Okay, that is not a good. It is actually very bad. You should not do that. If all the points of your measured, all the measured points of your experiment, if they are on a straight line perfectly, then your measurement is wrong, definitely wrong. Okay? So never do that. So your points will be distributed something like this in the graph. So now you have to draw a straight line. So how do you draw the straight line? So when I joined JEC, I asked the students, how do you draw the straight line? And then they say that some of them say that they connect 3 points. Some of them say that they connect 2 points. Some of them say that they just draw it within these points. Okay, so that's not scientific. You cannot just draw a line. Andazat, you cannot do anything just by some idea. It has to be scientifically backed, right? It has to be scientifically proved if you're doing something. So that's why we do least square fitting. See, if you just draw a line like this, suppose you draw this line, and this solid line should be the actual line, but you draw the dotted line. In that case, your slope will be different. So your result will be different, definitely. So you need to find a proper way to draw this line. That's called the least square fitting. Fitting of data. So for today's purpose, we will look at this example. So before that, let's check what is least square fitting. So suppose you have some measurements of data points x, y. Okay, x1, y1, x2, y2, xn, yn. All these data points. Okay. So you have these data points. You have to plot it in the graph. So x and y axis. Okay. And you want to fit it with a best straight line. So your best straight line will be y equal to bx plus a. So what you have to do is you have to find the value of b and a. So can you find that? The answer is yes, you can find that. What you have to do is to minimize chi-square. So there is a quantity called chi-square. So for a straight line, chi-square is defined like this. This is chi-square, sum from I equal to 1 to n. So there is this function. This function comes from this straight line. Okay, you have to divide it by the standard deviation. Okay, so you have to minimize this chi-square to find the slope b and a. So how to minimize some function? You take a derivative. You take the derivative and you equate the derivative equal to 0. So that gives you the minima of the function. That's how. That's why we take the partial derivative of chi-square with respect to a and b. Okay. Take the partial derivative of chi-square with a and b. So it gives you this function. After taking the derivative, we get this and this. and we equate them to 0. So this gives us two equations, right, involving some variable a and b. We have two equations and two variables. Solved it. After solving, we will get these two variables, right? A equal to this guy, b equal to this guy. Okay. So now from your data, you can measure this sum of x square, sum of y, and sum of xy. Okay. In delta, then you can find a and b. So finding a and b will give you the slope and the y-intercept. So if you know the slope and y-intercept, you can easily draw the straight line now. Simple. Okay, so this is for straight line fitting. So similarly, this method can also be extended to this 1 over x square line, y equal to x square, parabola, hyperbola, everything, polynomial, everything. But do not try to fit exponential. It's not recommended. Okay, so the example here. So I have this data set, okay, from some real experiment. This is again from this pendulum experiment, I think. I don't know. Let's see. Okay. Oh, no, not pendulum. This is a spring mass system. Okay. Suppose a spring is hanging vertically and you put a different mass on the bottom of the spring. The different masses actually. Okay. So that means you are putting load in the spring, and the spring will give you some deviations in length. That length will be extended. Okay, so the length extended is written as y or li. Okay, and the load you are putting is x or mi. Okay, and these are prime numbers. So for 2 kgs, your length is extended by 42. For 4 kgs, 48. For 6 kgs, 51. Something like that. So we will need this to calculate to get the perfect straight line. We need a and b, right? And for a and b, we require sum of x squared, sum of y, sum of x, and sum of xy. So we have to calculate these guys. That's why we square this mass, mi squared. So squaring this mass gives us x squared, okay? And we also take the product of x and y. So mi and li, okay? So this m squared, 2 squared is 4, okay? And 2 times 42 is 84. So this gives us mi li. So for every trial number, we take m squared and mi li. Then we sum them. So summing these x quantities gives you sum of mi. Summing these y quantities gives you sum of li. So for m squared, this gives you sum of m squared. And mi li gives you sum of mi li. Okay. So now you have everything that you need to calculate the slope and the intercept. Okay. First, you calculate this delta quantity. Delta quantity is in the denominator here. Delta means n times sum of x square minus sum of x whole square. So it is 200 from our data here. Then you calculate a. This is given in the equation here. So a is, if you put everything here, you will get 39.0 cm. There is a mistake here. There is an equal sign. It should be minus sign. Again, you calculate b. You put everything here. You will get 2.06 centimeter per kg. So now you have everything. So b is your slope, 2.06 centimeter per kg. And a is this y-intercept, right? So now if you have y-intercept and slope, you can easily draw a straight line, which will go through these points. So this is the actual required straight line that you need to produce in your results, in your data. All right. Okay. So I hope you have understood this point. So I'm going to show you how to do it in the computer by not doing all these calculations, but by not calculating everything here. Simple calculations. I'll show you. So finally, we have the summary. Okay. So we learned what is systematic error. We learned random error, uncertainty, accuracy, and precision. So I will give you these slides. So maybe the organizers can send you this slide by email or something like that. So I will give you this slide. You can go through it if you require. for your lab experiments later. Okay. So this is the general formula summary. So I also will give you this list. It contains some functions, their partial derivative, variance, and standard deviation. Okay. And the summary about statistical error. So this is just a simple cartoon. If you read it, you will understand. It's like a meme. So these are the references. So this book, the first one, An Introduction to Error Analysis, John Taylor, is very good book. If you can find it online, you can read it. It contains a lot of information. It's very easy to read if you would like to read it. Then there is 3 other books. You can also go through it, but I would not recommend. So I don't know if college libraries have this kind of books or not on error analysis. Maybe I checked JEC's library. It's not there, this book. But maybe you can have copies in your colleges. So this is the end of the first part of my presentation. Okay. So any questions? If you have any questions, you can ask me now before I proceed to a bit more fun part.
Excuse me, sir.
Yes, sure.
Can I say something?
Yes, yes.
Actually, I am not a student. Therefore, I would like to share something. Okay. You have described a nice presentation on the error, the precision, the uncertainties like this. But how can it possible to correlate with the virtual lab concept? We are waiting to know something or to learn something on virtual lab. So
yes,
is there any correlations?
Yeah, I mean, there is actually, so.
No doubt, there is a relation between there is a relation between the error and the measurement, because the physical science or the whole science is based on the measurement. You can say physics is a subject of measurement like that. But we are waiting to learn something on virtual lab. But how can it possible to correlate these ideas on virtual lab concept?
That's what I'm going to tell you now in the second session. Because see, in every experiment, this error is always associated, right? It's very important.
Yeah.
So you can also do this on a computer and present it to your students. So that's how we were doing it this semester in JEC.
Yeah.
Okay. So if you are ready, then I can proceed. Maybe if there are more questions, I can answer. Not. Proceed. I will actually show you how to take the data from the virtual lab experiment and analyze that data on computer.
Okay.
So, any more questions?
Okay, then I would like to thank Mr. Dr. Hrishikesh Chakraborty for your valuable talk.
Yes, I have one more part, like half an hour more I will take.
Okay, then you proceed.
Yes, okay. So, yes, so I told you how we can measure things, right? Take the uncertainties from experiments. So let's see how to do that. So first I'm going to talk about this experiment on Newton's ring, calculation of wavelength of light, right? By the method of Newton's ring. So this experiment is in virtual lab, vlab.omrita.edu. Okay, so the aim is to measure the wavelength of sodium light. We used to do this in the JEC labs, but since college is closed right now because of the pandemic, we are working on this virtual lab platform. So I will not directly go through this whole theory and everything. let me directly show you the formula. Okay, so this is the formula. Lambda here is the wavelength, okay, of whatever light you are using in the experiment. And dm plus p and dm, so these are some rings, the diameter of Newton's rings. Okay, you can find this from the simulator. I will show you. And then this r is the radius of curvature of the lens. There will be a lens, convex lens, radius of the lens. And p is the number of order of ring. Okay. So here it is given. You can just go through this whole theory and read about it. But I will show you. Directly go to the simulator. You can still see my screen, right?
Yes, screen is visible.
Okay. So this is the experimental setup, right? We have, so the inside of this experiment is not visible. So there is a glass slab and a plano-convex lens inside, okay? And there is a medium. You can select a medium here. Different types of mediums are there: water, acetone, isopropyl alcohol, and kerosene. So we'll just select air. And the light source we will consider sodium. Okay? Sodium is good. And we have these vernier scales in this instrument. So using these vernier scales, we can measure the diameter of the rings. Okay. And let me increase the radius of the lens so that the diameter increases. It's actually easier when the radius of lens is higher. Microscope position is okay. So now I will switch on the light. So I have switched on the light and you can see the rings in this part. Can you see the rings? The rings are here. There is this knob. You can change the focus. If I keep it here, the focus changes. Okay. So this is good, I think. And by changing this knob, you can change the position. Okay. Like this. So what we will do, we will measure the diameter for 4 different rings. Let me show you here in the procedure. See, we can have readings like this. So order of the ring, it will be like 4, 6, 8, 10, 12, like that. 4th ring, 6th ring, 12th ring, 10th ring, like that. And microscope readings, first we will take the readings in the left hand side, then in the right hand side. Okay. Then if you subtract the left hand side reading from the right hand side reading, this will give you the diameter of the ring. Okay. And then you can square the diameter. Okay. You can square the diameter here. Then you can plot the diameter in the graph. So let's see that. How to do that? Let's see. Again, I will increase the radius of curvature. I will switch on the light. It's focused. First, you have to measure the vernier constant. Okay. Here, just align. I think you all know this, how to measure vernier constant. Like align this 0 line with one line of the main scale. You do everything. That will give you the vernier constant. After getting the vernier constant, you position your. There, can you see there is a cross here in this window? If you can see the cross here, let me change the position. The microscope. So I'm taking cross here by moving this knob. So this is your second ring, right? The second ring here. So now my crosshair is on the second ring. you can take the main scale reading and the vernier scale reading here. So this will give you the left hand side reading for the second ring. Okay. Then again you go to the fourth ring. So this is third ring. This is fourth ring. Then you take the main scale reading, vernier scale reading. Similarly, 6th, 10th, 12th. It's up to you how many rings you take. But the higher you go, it becomes difficult to take the reading. Similarly, you go to the other side, in the right hand side, take the readings. You have to repeat it for the second, fourth, sixth again. Here, this is second ring. Okay, you take the main scale reading, vernier scale reading, you put it in your table. Okay, then you go to the fourth ring, put it in your table. Sixth ring, same, main scale, vernier scale reading. So you will have some data. Okay, number of rings, order of rings, and your diameter of the ring. Okay, so I already have taken the results so that I do not waste a lot of your time. So I already have this data. Can you see my screen? There is a text file here. There is a text file with some numbers. All right. So I will tell you how to analyze this data and find out how to do the fitting, least square fitting using this data. So since right now we have this pandemic and we cannot go to college, so it is not easy to do the experiments. And experiments are not accessible to everyone. Some students may not have good internet connections. They may not be able to open this VLab in their laptop or their phone. In most of the old phones, there is no Java support, so browsing this kind of websites is not possible. Yeah, we have students from all over Northeast in JEC. Some people from hill states. They have very bad internet connection, so they cannot open this website. That's why what we do is we give them this data. Okay, we explain the experiment to them, and we give them this data. Taking the data is one thing that is important, but analyzing the data is more important. I think it's very important. So that's their assignment. They have to analyze the data. We give them the data, and they have to analyze. So here I have written my data set. So this is for second ring, fourth ring, sixth ring, 10th ring, and 14th ring. So I have taken data for 4 rings, and this is the diameter. The second column is the diameter, 0.17, 0.377, 0.486, and 0.57. Then the third column is the square of the diameter. Okay, so what I have to do is I have to plot the order of the ring and the square of the diameter. Okay, so then from the formula, we need this P and dmP squared minus dm squared. So the ratio of these two things is the slope. So lambda, that's the slope. So we have to find that slope from the curve, right? So we are going to do that. So if you can still see my screen, you can see there is a text file. I have prepared the text file, and on the other side, I have my terminal. So in the terminal, I'm going to open a software called GNU Plot. So GNU Plot software, you can also download it to your computer. Just search for GNU Plot in Google or any operating, not a search engine of your choice. So GNU Plot, GNU PLOT plot. Just search for it. The first link, go to the first link, and you can download it from this website. So let's go to this download link. This will give you some links where you can download this software. So after downloading this software in Windows, or if you have a Linux laptop or Apple laptop, it's supported everywhere. Just go there, or you can also use your preferred plotting software. If you use other softwares for plotting, you can also use that. But I use GNU Plot. I have taught my students to use GNU Plot. It's a very simple, lightweight, like less than 10 MB. So people with bad internet connection can also download this one. Okay. So now I will try to plot this data. I will go to my directory where this data is located. These are my data files. Here I have the data. This is Newton's ring.txt, this data file. So here I will start GNU plot software. So GNU plot software is started. So let's plot this first data set and the third data set. So there are commands. I will give you the commands if you give me, I don't know, I will give this, all the files that I use, I will give this to the organizers and they will distribute to you if they can. So the command is simple, just plot. Okay. So what we are going to plot? We are going to plot this data file. So the name of the data file is Newton's ring.txt. So under these columns, we have to write Newton's ring.txt. Okay. Using, we have to specify which column we are going to use. So we are going to use the first column and the third column. So using 1:3. And I want to plot a line with line. Okay. So now if I press enter, this gives me the plot. So see, very simple. If you have the data file, you enter one command, this gives you the data. And this gives you the plot. Okay. Connecting all the points, but this is still not a straight line, right? We have to fit it. If you do not want to plot a straight line, you just delete this width line extra flag. This is called the flag, width line. Just delete this and then press enter. This gives you the data points. Okay. So here in GNU plot, you can also set the axis. Okay. First, I will set x-axis, x range actually, range of x-axis. So that will be from 0 to 15. And range of y-axis. Y-axis is range from 0 to 0.35, suppose. I'm setting my axis. Then I can name my axis. Set x level. So order of ring, right? Order of ring. Set y level. Diameter squared. I would also like to set the grid. The grid in my plot. Okay. Now let's plot again. Okay, it gives me, you can see the plot. It gives me the data points here, 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 and here. All the data points. In the x-axis, we have order of ring, y-axis, diameter squared. So now we would like to fit this data with some straight line. So for that, we have to first define a straight line. Okay, let's define a straight line. So it is fx equal to a1 star x plus star means multiplication here, plus a star x plus b. Okay, I have defined my straight line. And for fitting, the command is this one, fit fx data.txt using this everything. Okay. So fit fx, fit my line xx fx that I have just defined with Newton's ring.txt using 1:3 via the parameters A and B. So now I have defined the command for fitting and I have pressed enter. So all those calculations that I showed you in the PPT, the computer program does it by itself. So you do not have to do that. And it gives you the results, A and B. So A and B, A is our slope, B is our intercept. So the slope is 0.02455 and the intercept is 0.0139. It also gives you the chi-square actually. So if those people who would like to have chi-square, you can have the chi-square from here. All right, so you know your A and B, slope and y-intercept. Now you can plot your actual fitted line with the data. Right? Now let's plot it. Plot. Sorry, fx and your data points. It's from here in the txt using 1:3 and let me give it a title. String. Now if I press enter, it gives me this plot. Okay, here you can see in the plot, these are the data points across here, 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 and here. Okay, and this purple line is the best fit line. Okay, now from this plot, you can find whatever you require for your calculations. You go to the formula. What you need is this dmp squared minus dm squared. So just consider any 2 points on the graph. Okay, that would give you the diameters. Okay, suppose you go here 12. Okay, for 12, order of the ring 12, you find what is your diameter. For 8, order of the ring 8, you calculate the diameter squared. So those diameters squared, the difference in that diameter squared will come in the numerator. And 12 minus 8, which is with P. So 4 will come in the denominator. So you put everything there, then you can calculate your lambda. Okay, and since you have a chi-square from this fit, so that means you can also calculate the error associated with lambda easily. All right, so this is how you implement this error calculation things in a virtual lab, fitting, doing the error, everything. You can do it in the virtual lab. So similarly, we have another experiment, this one, Newton's law of cooling. So this is not in virtual lab, this is in olab, olab.e2.in. Okay. So here what we can do is we can verify Newton's law of cooling. We can also find a specific heat. So actually this experiment in the theory, if you go to the theory, it's not actually for calculating the specific heat of the liquid, but we have modified it in our class in JEC. We have modified it and we have given them a different manual so that they can calculate the specific heat of the liquid. So what we tell them to do is to find the cooling curve for two liquids. Suppose for water and for some other liquid. I think here there is milk, vegetable oil, and olive oil. So for milk, it is a bit cumbersome to do because the plot tries to overlap with the water plot because the specific heat of water and milk is very close, right? It's 0.9 and 1. So you can do it for vegetable oil. Okay. So what you have to do is you set the material of the calorimeter for copper. Radius and mass of the calorimeter keep it same. Use this vegetable oil as liquid. First you do it for water, then you can do for vegetable oil. So the temperature of the preheated liquid, you take it to 80 degrees Celsius. And room temperature, here the room temperature is obviously like 35 now, but let's imagine we live in a good and nice place where the room temperature is 25. Now you can start the experiment. It gives you the temperature here. You can see, you can measure the temperature here also, and the time here. So you will have a graph of time and temperature. So the cooling curve you will have. All right. So in this experiment, you can also see what's inside this calorimeter. So there is a stirrer. The stirrer is making the heat uniformly distributed in the liquid. You can also, if you want to see, you can also see the graph. If you go on, it will keep calculating the graph like this. Okay, so first you do it for water. You calculate temperature with respect to the time. So at every time, like after 5 minutes, after every 5 minutes, you calculate the temperature for water. Okay, then you reset it. You do it for vegetable oil, maybe. Do it for vegetable oil. Again, you have to take the temperature to 80 degrees Celsius, room temperature to 25. Okay, you can start. So see here, the mass of the liquid is given, a specific heat of the liquid is given. So imagine you do not know the specific heat and you did not check it here. Just note the mass of the liquid, mass of the calorimeter, okay, and specific heat of the calorimeter and specific heat of the water. So if you know all these quantities, you can, there is a formula, from the formula you can easily calculate the specific heat of the liquid, okay, vegetable oil. It's cooling very fast for vegetable oil. Okay, so I also have the data for this. I asked my students to do it by themselves. So actually, if you see in this experiment, it's very hard to measure the time and temperature simultaneously, right? Because they are changing together at all times. It's very hard. So what I asked them to do is take screenshots after every 5 minutes. 5 minutes here in this stopwatch, not the real 5 minutes in real life. Here, after every 5 minutes, I have asked them to take the screenshots. So the screenshot will record the temperature and the time here. So you have a data set. I have the data set with me. I have asked my students to send me the data set. It is here. You can see. So the first column is for water, I think, and the second column is for the liquid, the vegetable oil. And this column is for the time. So in minutes, actually, the 0, 5 minutes, 10 minutes, 15 minutes, to up to 100 minutes. So it has recorded the temperature at these different times. Okay, so we can also plot this in GNU plot. Let me clear this part. Okay, so plot. I would like to plot this data file in cool.txt using 1:2 with line. And again, same file again I want to plot. This time using 1:3, first and the third column with line. Press enter. Doesn't show me anything. Why? I don't know. There is some problem. Wait, let me check. Okay. Because okay, so here's my data. So one plot here is for water One plot here is for vegetable oil. So what teachers can ask the student to do is to make this kind of plots if they have access to computers. And if they do not have access to computers, you can give them the data. If they are not able to take the data, you can give them the data. You can ask them to plot these graphs. You can ask them to calculate the error from these graphs, okay? Because there will be error associated with the time measurement device and the temperature measurement device. Okay, so that would be 0.05 degrees Celsius, okay, and 1 millisecond maybe for time. So error analysis can be implemented in this kind of exercise, in this kind of experiment. You can just, if there is no way to access the labs, I would suggest that just give them the data so that they can learn how to analyze. Because you see, nowadays, if you go to any big lab, like, I don't know, in my case, I worked in astrophysics before, but I have never been to a proper astronomical observatory. I have never been to Chile because there is a big telescope at Chile, but I have taken the data from Chile. I can access that data from my computer, from the data of the telescope. I can access the data of my gravitational wave observatory from my computer. So it's also very important to learn how to analyze the data. So I have seen students, even in JEC, they do not know what is error, how to calculate the error. Okay, and if you go to some higher education institute and if you do an experiment there and you do not calculate the error, nobody will believe you. They will not, your result will be totally discredited. So I think it's very important to learn the error and learn to implement the error in real lab or in virtual lab. Okay. So yes, yes.
Can I say something?
Yes, sure.
Yeah. Actually, what is happening? What you have shown in suppose Newton's ring experiment,
yes.
Several data are found and a set is found, and after that we can plot and finally we can calculate the result as well as we can calculate the errors. Yes. But thing is that it is not known to me. It is a doubt for me that whenever two students will perform the same experiment with the same instrument. Suppose radius of curvature of the plano-convex lens, it has a certain value, and the rings are supposed from 10 to 19 ring diameters are taken. If same rings and same data are taken, is it the results are same?
No, it
whether
won't
the
be same
results are same or not.
No, it won't be same because the results will depend on the observer. So I will give you the example here. Suppose I go to this simulator for Newton's ring, sodium, radius of curvature suppose 85. I switch on my light. So let's go. Let's fix this in a second, or maybe. So error will come up when I try to put my cursor on the ring. Okay, it will not be same for all of us because there will be parallax. There may be some error. Okay, so I have put it in the second ring. Then now I can see the result in the vernier. What is my vernier scale reading? I can check. So my vernier scale reading, to me, it seems it's 7. I think 7. So what do you see in your screen? Can you tell me what? Maybe you will see 7 or maybe 9 or 10. So that's how the results may vary, right?
But instrumental errors are not coming. So.
Yeah, instrumental error, it's very, since this is a simulation, it will be very hard to find the instrumental error.
Yeah. That is I want to say.
Yes. So instrumental error, you have to, so since you are a teacher, it's up to you. You can simulate the instrumental error, just like you're simulating the data, right? Yeah. So if you are giving your students some data to analyze, you can also give them that this result has this much error and calculate how this error will propagate to the final result, right? So that's a good exercise, right?
Yes.
I don't know what you think, but yeah. Okay.
Thank you.
But of course, nothing can replace a proper lab, right?
Yeah, that is correct. Yeah. Actually, what I am thinking, in our usual lab, two parts are there. One, suppose students and teachers are there, and also the instruments are there. But in this virtual lab, third part is again coming, the programmer as well as the simulator. These are the third parts. And
yes.
With these three parts, we can perform our experiment actually. Is it correct?
Sorry, I did not get you.
So, yeah. Actually, three parts are there in virtual lab, I think.
Mm-hmm.
We are the students and teachers are there. These are one part. And instruments are there. These are second part. Simulators or the programmer. These are also third part of the same experiment, I think.
But here in virtual lab, the programmer, the simulator, who is writing the code, he is the instrument actually. So it's
okay. Mm-hmm.
So yeah.
Thank you, sir.
Yeah. So any more questions, students? I would like to have some questions from the students. Okay, so the organizers, I will give you the presentation. I will send it to Dulan sir. So could you share with the students if possible?
Yes, definitely. We'll share it.
Okay, I will send you all the text file, the link for downloading GNU Pro and everything.
Okay, thank you.
So I will stop sharing my screen. I think it's stopped, right? Yes. So any more questions? If you do not have questions, I think I'm done.
Now, I would like to thank you for your valuable talk, sir.
Thank you.
You have described how to minimize the error and importance of uncertainty, systemic error, random error, how to do addition, subtraction, and multiplication, what is fractional relative uncertainty, and propagation of error, relative uncertainty, statistical analysis of random error, and data analysis. And you have also described about the Newtonian apparatus and then Newtonian schooling also. Thank you, sir. Now we have another speaker is waiting for this session, and Professor Rakesh Baid, Department of Electronics, University of Jammu. I welcome you, sir, in this program. So you can proceed now for your talk.
Yeah. My voice is audible?
Yes, you are audible, sir.
Okay. So thank you very much. So yesterday I delivered a talk on the microprocessors, how to do practicals using virtual platforms. So today also we will continue with the same, and 8085, yesterday we did 8085. Today also I will take some example using 8085, and then we will go to 8086. That is 16-bit microprocessor. So now I will share my screen. Is some screen is visible?
Yes, sir.
So can you tell me what you are able to see on the screen? Is it this one?
Screen eating snake game.
Snake game. Okay. No, not this one. Just 1 minute. Okay, are you able to see 8085 simulator?
Yes.
Yes.
Okay. So, dear students and all the respected faculty members who have joined this session on microprocessors. So basically, because this is one of the very important course in post-graduation and in the engineering also, and I think now BSc students are also studying sometimes microprocessors in their final year. So it is very, very important. So I will just, yesterday we have seen some examples on microprocessors. So today also we will see 1 or 2 examples, and then I will quickly switch over to 8086 programming. So this is 8085 programming. The example which I have loaded is basically about the ones complement of a 8-bit number. Ones complement. So this is the program. This is the ones complement of an 8-bit number, and the number to be complement is stored in C050 location, and the answer is stored in C051. So the number which we are going to complement is in C050, and the answer is answer will be stored in C051. Okay. So this is the program. So first what we do is we load the accumulator with this contents of this location, that is C050, and then we simply complement this. CMA is the instruction for the complement, and after the complement again we store the result STA. STA is for the storing the result. STA stands for store the contents of the accumulator in C050. So the first LDA is also a 3-byte instruction. LDA is this is 3A. 3A is the hex code for LDA, and then C050. As I told you yesterday also, first we load the lower order byte, and then we load the higher order byte, and then CM is complementing of the accumulator contents, and then we want where we want to store the result, that is C050, we want to store the result. Okay. So now if I this, let us say C051, C050, let us say it is FF, and C01, it is 00. Okay. So let us do it step by step. So I think this program is not executing as per the program. There may be, I suppose there is some error. Let me try some other program. Uh, just 1 minute. So this is another program. This program is about the two's complement. The difference between one's complement and two's complement is that we add one in the one's complement. So after that we add one in the answer, and that becomes two's complement. So here you see, let me just execute the program. So you see, the number was 96, and the answer is 6A. So you can see, one's complement is basically, one's complement is all the ones will be converted into zeros and all the zeros will be converted into ones. So 9 means 1 0 0 1, and 6 means 0 1 1 0. So one's complement of this number will be 0 1 1 0 1 0 0 1. And if we add 1 into this, it becomes 1 1 0 1 0 1 0 1 1 0. So it is 6A. Okay. So let us take a simple number. For example, if I take a number as 0 1, and then the answer is FF. 0, the ones complement of 0 1 is 0 0 0 0 1, and then it is F. Yes. So you can see the number which we have given is 96 and the answer is 6A. So I think this is the correct answer. So in this way, my whole idea is that in this way we can do all the practicals whatever we want. Even there are some subroutines that we can upload some subroutines also with some interrupt subroutines, that is this is trap RST 7.5 RST 6.5. So all these subroutines can also be loaded onto the computer. We can also see what is there in the memory. We can see the contents of the register, and we can also see what is on the IO ports. So I request the students to upload, to load this simulator onto their systems, and then they can try uh, different programs to learn programming of the using 8085. So I think there are many examples are given. So students can use these examples to learn the basic programming of the 8085. So since we don't have much time, so now I will just take I will just let you know about the 8086 microprocessor. So for that, I am exiting this screen, and I will be sharing the screen again. Yeah. So is my new screen is visible now?
Yes, visible, sir.
It is this documentation index license tutorial 8086 instruction. Is it this?
Yes, sir.
Okay. So so for all of you, now this is a 8086 emulator, and this is the documentation about this emulator. So let us just study little bit about this. So first of all, I just wanted to tell you about the 8086 instruction set. So, as all of you know, 8085 is basically an 8-bit processor, whereas 8086 is a 16-bit processor. So, when we say 16-bit processor, it means now the data we can handle at one time, that is 16-bit. We can add 16-bit, we can subtract 16-bit, and so on. We can do all sort of operation using 16-bit data bus. So, inside the CPU, in 8086 we have now registers like AX, which can be used as a 16-bit register, and if we want to use uh, as an 8-bit register, it can be used as an AH and AL. AL is the lower 8 bits, whereas AH is the higher order 8 bits. Similarly, we have BX register, BL and BH. BL can be used as an 8 bit, and BH can be also 8 bit. So mean if BX is used, then it is 16 bit. So means for 16 bit operation, if we want to use a 16 bit register, we have to use BX, and if we want to use 8 bit register, then either we can use BL or we can use BH. So BL and BH, they can both be used as an independent 8 bit register. Similarly, we have CX, DX. So whenever we have AX, BX, CX, DX, it means these can be used as a 16-bit registers, whereas whenever we use AL or AH, BL or BH, CL, CH, so these are all 8-bit registers. So in addition to this, we have registers like this is CS, SS, SP. So basically, for all the students who have studied this, the whole memory in case of 8086, because 8086 microprocessor is a 20-bit address lines. It contains 20-bit address. So the memory capability it can handle is about 1 MB. So 2 raised power 20 is 1 MB, because the memory capability of a microprocessor depends upon the number of address bits it has. 8086 has 20 address lines, so it can handle a memory up to 1 MB. And moreover, the memory organization in 8086 is like that the whole of the memory is divided into various segments, and one segment size can be maximum up to 64 kilobyte. So all these segments, what is the top address of the segment, that can be seen from the segment registers, and there are 4 segment registers like here you can see CS, SS, SP, CS, SS, SP, and you have ES, ES, DS. So these are the segment register: ES, DS, CS, and SS. Code segment, stack segment, extra segment, data segment. And these are the some other register. SP is used to point the stack segment register, that is a stack pointer. And BP is the base pointer, SI is the source index, DI is the destination index. So these are the basically index registers. So AX can be used as an accumulator, and BX can be used as a BS register. CX as a count register, DX as a data register, SI as a source register, DI as a destination register, BP as a base pointer, and SP as a stack pointer. So now, as I told you, there are segment registers like CS, points at the segment containing DS, generally points at the segment where the variables are defined. And ES is the extra segment register. It is up to a coder to define its use, that is extra segment. And SS is the basically segment containing the stack. So I have already told the students and the audience now that because our total memory capability is 1 MB, but the segment size can maximum be 64K, then how we can calculate the physical address of the memory. Physical address of the, to calculate the physical address of the memory, but we have to multiply the segment register. We have to multiply the segment register by 10H. That is basically this is in hex, but in decimal it is 16. So basically multiplying 10 means simply adding 10. For example, the segment register is 1030. So when we add one more zero on this, so it means you simply add 10 and then add the offset address. Offset address means whatever is the address of the source register or some destination register or whatever it is. So that is how you can calculate the physical address. So I will repeat again, physical address can be calculated by adding the effective address or the offset address into the segment register by appending 10 on its right side. So if you append 10 on the right side and then add, you will get instead of 16-bit address, you can get 20-bit address. So that is how you can calculate the physical address. So the address formed with two registers is called an effective address. By default, BXSIDI register work with DS, that is the data segment register. BPSP work with the SS register, that is the stack segment register. Other general purpose register cannot form an effective address, and also BX can form an effective address. BH and BL cannot. There are special purpose registers. IP stands for instruction pointer, and whereas flag register that give us the status, that what type of function is going on, what type of operation has been done. So flag register always give us the status that what type of operation has been performed. Okay. So this is little about the 8086 assembler tutorial for the beginners, and similarly you have '8086 instruction set. So broadly speaking, 8086 microprocessor, or for that matter any microprocessor, whole of the instructions can be divided into depending upon the operation we want to perform. So one is known as the arithmetic and logical instructions. For example, instructions like add. So here you can add two numbers. ADD, ASCII just before division. So there are so many instructions. One has to, this is add ADD. You can add one operand with the other operand. For example, move AL05, then add AL-3. So means the result will be 2, right? Similarly, this is ADC, add with carry. So before going to the programming, one must be familiar with the instructions. This is AA, ASCII just after addition. So means how you can adjust your answer, ASCII adjust after addition. That is correct the results in AL and AH after addition when working with BCD numbers. BCD numbers are basically from 0 to 9. It works according to the following algorithm. If the low nibble is of AL greater than 9 or AF is 1, that is auxiliary flag is 1, then AL it becomes AL plus 6. So basically what happens is 6 is added into the nibble so as to set the results according to the BCD form. So there are so many, instructions. These all instructions are basically jump. Jump above bar equal. If carry flag is 0, then jump. If carry flag is 1, then this jump will not be executed. Similarly, you have, this is the most important thing, that is jump on carry. If carry is 0, then jump. Jump on carry. Short jump if carry flag is set to 0. Similarly, you have short jump if the operand is not equal to second operand. So means 0 flag is 0. If 0 flag is 0, then jump. Otherwise, this instruction will not be executed. So what I mean to say is, all the students, you have to become yourself familiar with all sort of this instruction. This XOR means logically exclusive OR between all bits of two operand. For example, these rules apply. 1 XOR 1 is 0. When the same bits are XORed, then the result is 0. When they are different, the result is 1. So means the truth table which you already know about the exclusive OR gate, same truth table prevails here. So you can do whatever you want. So this NOP means no operation. NOP instruction is just added to increase the delay in the program. You add NOPs, number of NOPs, they will be it will do nothing. It will simply be added to increase the program length, or if you want to add some delay, you can add NOPs. That is no operation. So basically, no operation will be performed when NOP is used. Then you have this RCR, that is rotate operand 1 right through carry. So you can rotate the number by using this instruction. Rotate operand 1 right through carry flag. So means the number will be routed through the carry flag. The MSB will go to the carry, and the carry will go to the LSB. MSB will go to the carry, and the number of rotates is set by the operand 2. So these are the sort of instruction: move SB, move string byte, move string word, load string byte, load string word, load string, this store string byte, store string word. So instruction in the CX time, that is the counter. Basically, how many times you will repeat this, that is the basically depends upon the number which you put in the CX register. So means counter, whatever the counter you want to set, that number you have to put in the CX register. So I will show you some more instructions. So these all instructions which start with J, these are the jump instruction. These are basically these are all conditional jumps. So mean, if the condition is true, then and only then the jump will be executed. If the condition is not true, then the jump will not be executed. If the condition is not true, then the jump will not be executed. Similarly, this DIV ID, this DIV is the division, basically unsigned divide. So you are going to divide two number, but unsigned means you are taking only the magnitude into consideration. The number is treated as unsigned number. So when the operand is byte, AX divided by the operand, the result you get in the AL, and the remainder you get in the AH. And when the operand is a word, then it is DX and AX, mean lower order byte is in the AX register and the higher order byte is in the DX register. And the A result you get in the AX register and a remainder you get in the DX register. For example, you can see here, this is the operand, and now this will be divided by the AX. So DIB BL means now, because BL you have 4, you are dividing this data by 4. So the only difference is DIB and IDBI is the signed divide. I must tell you what is the difference between a signed number and unsigned number is that for a signed number, the MSB of the number is its sign. For example, an 8-bit number, the 7 bits are used for its magnitude and the 8th bit is used for its sign. For example, if the MSB is 0, MSB stands for the most significant bit. If the MSB is 0, then the number is treated as positive. If the MSB is 1, then the number is treated as negative. Right? So this IDBI is basically signed divide. Now similarly, these instructions compare SB. So this instruction compares two numbers. That is, here SB means byte. You are comparing 2 bytes. And then it is SW, it means you are comparing words. Byte means 8-bit data and word means 16-bit data. That is the only difference. You are comparing two numbers. Similarly, you have CW, convert word into double word. So what you are doing is converting a word into double word, right? So when you are converting a word into double word, so what happens is, double word means the higher order value will go to DX. If a high bit of AX is 1, then DX will become this. That is 0 FFF. All the bits will be FFF. 1. Means whatever is the MSB double word, it is a word extension. Mean if your number higher order bit MSB is 1, then the higher order byte that will become all ones. That is FFFF. So means you are basically converting a word into double word. So this way we can learn about all the instructions of the microprocessor first. So means if we are able to learn about the instructions, then we can write the program. So these are some important points. When two operands are required from an instruction, they are separated by comma. Mean for example, register, comma, memory. when there are two operand, both operand must have the same size, except shift and rotate instruction. For example, this is very important. For example, if we are moving a number from one register to another register, then it is very much compulsory that the size of both the register must be same. For example, we can make a transfer from DL to AL. We can make a transfer from AX to DX or DX to AX. But we cannot do from DL to AH. Sorry, DL to AX. Because in that case, AX size will be 16 bit, whereas DL size is 8 bit. So we have the destination as well as the source, their size must be same. Similarly, some instruction allow several operand combination. For example, we can have immediate data that and the memory, immediate data and the register and the memory. We can have a segment register to the register. So this is also very important. So means when we say set means the value is 1. When we say reset, it means the value is 0. So that was the quick reference about some instructions, and then this we did. Yes. So this is also very important because basically there are addressing modes. Addressing modes means how we specify the data. Specify the data means the method how we specify the data, how we specify the operand, that is known as the addressing modes. And our offset values, they can be like this. You can have your offset bx plus si, bx plus di, bp plus si, bp plus di. So means there are very different combinations by which you can specify your memory. Okay. So the value of the segment registers CS, DS, SS, ES, they are the segment, and the value of the purpose register BX, SI, DI, BP, they are that is the offset. So means segment is to offset, and physical address you can calculate by putting 1 0 here in the segment register and adding these two numbers. So sometimes it is written byte PTR. It means it is a pointing, you are pointing to a byte. And by word PTR means you are pointing to a word. Word means 2 bytes, 16 bit. So for example, you have move instruction, you can have various moves. You can move between the register, you can move between the memories. Okay. So I think this I have already explained to you, but still I will just tell you because these flag registers carry flag, zero flag, sign flag, parity flags, auxiliary carry flag. So these flags, 5 flags were there in 8085 also. So, but in 8086 you have total 9 flags. In 8086 you have total 9 flags. So some of the bits they are don't care. So means they are not defined. Basically a flag is said to be set if its value is 1. So for example, carry flag, this flag is set 1 when there is an unsigned overflow. For example, when you add one number, when you add two number, and if there is a carry out of the MSB, then the flag is said to be set. Similarly, zero flag, if you get the answer 0, it means your result is 0, the zero flag is set. Sign flag is set, means the result is negative, and positive it is 0. For example, the MSB of your result is the most significant bit of your result is 0, then the number is said to be positive, otherwise the number is said to be the negative. Now overflow flag means if your destination, if you are not able to put the number into your destination register, it means if the operand is not able to fit into the destination, it means then there is overflow. Parity flag depends upon the number of ones in your answer. For example, if you have this flag is set to 1 when there is an even number of ones in the result, and it is 0 when there is odd number of ones in the result. So if the result of a number of a word only 8 low bits are analyzed. I hope you understand. Hello, sir.
Yes.
Hello. Yeah. So I hope my sound is clear.
Yes, you are clear, sir.
Okay. So then auxiliary carry flag means if there is a carry out of the first nibble. Mean if there is a carry out of the first 4 bits, then this auxiliary carry flag is set. So now what is the difference between this flag register when we compare 8085 and 8086? So here my point is 8086 has additional 3 flags, that is interrupt flag IF, direction flag DF, and there is one more direction flag, interrupt flag, parity overflow. There is one more, I think. Just 1 minute. So these are known as basically control flags, trace flag, yes. TF. Yes. So I think that is not given here. So here it is, trace flag, interrupt flag, and direction flag. Trace, interrupt, and direction. Basically, these three flags are known as control flags, whereas all other flags are known as condition flags. So condition flags are carry flag, zero flag, sign flag, parity flag, auxiliary carry flag, overflow flag, because they are based on some condition. If the condition is true, then the flag is set. If the condition is not true, then the flag is reset. But these three flags, direction flag, interrupt flag, and trace flag, these are basically these are control flags. Control flags mean direction flag we can set, because in 8086 we have two index register. One is known as source index, other is known as destination index. So we can have string operation that we can transfer a large number of data from one source to the destination. So in that case, we can set a direction that is from or to. That depends on the direction flag. So if a direction flag is 0, the flag is used by some instruction to process data chains. When this flag is set, the processing is done forward. When this flag is 1, then the processing is done backward. For example, if you set your source and destination. Then if you set the direction as 0, it will be done 0, 1, 2, 3, 4. Mean it will transfer your data from 100, 101, 102, 103 like this. And if the flag is 1, then the processing will be done backward. That is under 99, 98, 97, so on like this. And similarly, interrupt flag means if this flag is set, then you can receive interrupt from the external devices. For example, if you do not want that any external device can interrupt the microprocessor, then the interrupt system can be disabled. You can disable the interrupt system by making the interrupt flag is equal to 0. And similarly, trace flag is that is used for debugging the program. That is, when you want to execute whole of the program in one go, then this flag is set to 0. That is, your simulation, you can do the simulation of the program, or you can execute the program by simply, in a one go. But sometimes there is a error. There is a error in the program. So how to find that error? How to debug the program? So then in that case, you can make the trace flag is equal to 1, so that you can execute your program in the single stepping mode. So you can execute whenever you want to use your program in the single stepping mode, you can use the trace flag, that is for the single stepping. So I hope with this introduction, these are the basically some interrupt vectors. So in 8086 we have overall 256 interrupts. So some of the interrupts may not be used, and they will be used in the higher order, processors like 186, 286, 386, so on. So in instruction set, we have done interrupts, and then this is the basic tutorial. I think we have done most of it. So now let me take you to the simulator. So I am going to stop this content, and I am going to show you the simulator. Hello, sir.
Yes, sir.
Now, are you able to see this EMU 8086 sampler and microprocessor emulator 4.07?
Yes, sir.
Yes.
Okay.
Yes.
So, as we have seen the other simulator for 8085, so this is also a online simulator for simulating the 8086 programs, because the whole idea of this workshop is how to do all these programming online by sitting in your residences, by sitting in your homes, at your computer screens. Otherwise, normally what we do is we have all these kits in the labs, and we perform these practicals in our laboratories. But because due to this pandemic, we are sitting in our homes and we are not able to do the practicals in our labs. So that is why Professor Dulin Soki has organized this workshop, so that the students can be made aware, made familiarized that how you can do these programs online by sitting in your homes, by using these simulations. Of course, this whole idea may not be 100% satisfying, because unless until you do with your hands on the kits or using the equipments, that is the best idea. But under the circumstances, I think this is also very useful for the students, that you can have a feel that how you can run your program, how you can decode your program, right? So this is again a simulator by which you can do 8086 experiments. So we will just, I think we can load some examples. So one program I have seen, this is traffic lights. This program is basically for the traffic lights. So one thing I just wanted to tell you that this hash, whatever is written in the comments, within the comments, this is not executed. This will not be executed. For example, the first line you may be seeing controlling external devices with 8086 microprocessor, realistic test for C. So I mean these lines, they are not executed. So now this hash start traffic lights.exe, name traffic, move ex, comma, all red, out 4. So here out 4, move ex. So means here what is you can say all red. All red is data. That is move. All red is the memory location, or red. This is the data. All red. 000, this 001 111. So this data will be you have already defined all red. EQU, these are basically EQU is a assembler directive. When you say all red EQU 000, so mean it will equate all red to this number. So similarly, when you say DW, that is, it is defined word. You are defining a word of that. So these are assembler directive. These are the directives for the assembler. These are not the these are known as pseudo instructions. So whereas the instructions like this jump, move si, jb, that is jump on below, cmp, add, int. So these are the instructions of the 8086. Out 4 means you are outputting the contents of the AX on a port address whose address is 4. Right? So now, once you write the program, what you do is you compile this program and after compiling this program, you can run this program. So are you able to see the traffic lights like this?
No, sir. A black screen is there.
A traffic light is not visible, sir.
Which is not visible?
The black part is visible. Traffic light is not visible.
Okay. So this is visible demo version. Click here to buy this software.
No, sir, not visible.
Okay. Now, are you able to see some screen?
Yes, sir.
Yes, sir.
Now this traffic lights are there.
Yes, sir. Yes, sir. Now it is visible.
I think now whole screen is available. Now full desktop is available.
No. Whole screen is available. Whole screen is available.
Okay. This emulator traffic dot bin, this is also seen?
Yes, yes.
Yes.
Okay. So basically, this is actually demo version. So demo, this is saying that you have to buy this software for this. But I think just one. Let me execute again. Compile, save, and run. Now you are able to see the traffic lights.
Yes, sir, visible.
Okay, okay, yeah. I think this is the output of this program. But since this is a demo version, this may not work for some of the some of the programs. Okay, so let me explain. It is not working in the single step. So here I just wanted to tell that so by this way you have to load the program, you have to write the syntax. You can write your own program. You can add your code here, right? So you can write your own programs and then you can execute these programs. But I am not sure whether this will work on this. So let me add some other program. So the program which is written in the assembly language is the extension is .asm. So there is another example. This example show how to access virtual port 0 to this. These ports are emulated to file number this. So mean you can use various. This is the here. This is the port address 75678. This is the port address, and you are basically outing on this data on this. So the name of the program is LED. So when you compile this program and save, you can see some LEDs are glowing here. So instructions I can explain because this this is the out. Out instruction means the accumulator data will be outputted on that port address. The port number which you have given, that data will be outputted onto that port. And then move 1, 2, 3, 4. This data is moved into AX, and then you are outputting on the port address 199. So see, these are basically small ideas how you can run these programs, how you can get familiar with this type of programs using the simulators. And I think once we have a professional version, because I tried to find out on the net, this demo version is only available, but I am sure this professional version will also be available. And moreover, nowadays freewares are also available, so we have to do a little bit search, then we may get freeware also. This is just a moment. Okay, then one more examples. Stepper motor. So because we can do a lot many programs using this programming, but what we have to do is, yes, you can see we are getting a stepper motor at the output. Hello, sir.
Yes, sir. Yes, sir. Proceed.
Yeah. So I am only this much to show today because this is a demo version and we are not able to write our own program. So, but my whole point is that we are able to give the students an idea that how they can write the program and how they can execute the programs. So I have shown them 8085 also and 8086. But now, if they practice and they can get familiar with such type of programming in their own homes and at their residence or at their workplace wherever they want. So not in the lab, but they can perform these practicals on their computers.
Yes, sir.
Yeah. So if there are any questions, I can answer those questions. So basically, this 8086 simulator, this is a demo version. 8085 is working fully, but 8086 is a demo version. So, but it is saying that when we run any program, it is saying that you have to pay. So because I have not purchased this, so I think the college authorities or the universities may purchase. The cost is not much, or if somebody, but I think I am sure that freewares might also be available if we search. For example, when we compile, it is asking for the money. When we run the program, it is saying that click here to buy this software. So this is basically a demo version. Yeah. So that is all. Thank you very much for listening to me. I think I may be able to, make you understand a little bit. But if you have any questions, my whole idea, because this 8085 and 8086, they are complete one semester courses. So one semester course mean almost 50 to 60 lectures to understand the entire course, and even the instruction set, that is also not very easy. So in 1 hour it is very very difficult to make all the students understand. But anyway, my email is with the organizers. If because right now I am teaching this course to the MSc students, if anybody having any specific question regarding 8085 or 8086, they can write to me and I will try to give them a reply on their respective emails.
Okay, thank you, sir. Thank you.
Yeah. So Professor Julian Sakia is having my email address. So I will be very happy to reply all the queries with regard to 8085 programming, with regard to 806, their theory, applications, anything. If anybody wants any information regarding this, so I will be very very happy to answer and I will definitely reply their email. So please do write to me if you have any queries. So I think with this, I end my lecture and thank the organizers for giving me an opportunity to interact with you, interact with the students. Thank you, sir. Thank you so much.
Thank you, sir. Thank you. Thank you very much for your valuable talk, sir, about microprocessor 8085 and 8086. And you also explain how to use it. Thank you, sir, for your demonstration. Now, I request Mrs. Dipti Borahuya, Assistant Professor, Department of Physics, Jorhat Kendriya Mahavidyalaya, to deliver vote of thanks.
Am I visible?
Yes, yes. You proceed.
Yes. Respected Principal Sir, our most valued and worthy regards, respected Dr. Hishikesh Chakraborty Sir, Professor Rakesh Bhatt Sir, Academic Vice Principal of our college, and Convener Ili Ma'am, Coordinator Naki Ma'am, Head of the Department of Physics, Rajiv Bordloi Sir, and all the participants of this webinar. It is fine for me that I am proposing a vote of thanks for this technical session. At the very outset, I am proposing a thanks. I am behalf of organizing committee JKM National Lab webinar express deep sense of gratitude to the chairperson, our principal sir, Dr. Dulen Soikia sir, who was the brain behind in organizing this webinar. My sincere thanks to respected speakers, Dr. Rishikesh Chakraborty sir, Assistant Professor, Department of Physics, Jorhat Engineering College, respected guest of honor and speaker, Professor Rakesh Bhet sir, Department of Electronics, University of Jammu, who delivered to us valuable speech in today's technical session which successfully. Then I want to thank all the participators, including students of our college and other institute also. Even I want to thank those participators who participate indirectly through their respective participators, such as someone's family member, friends, etc. My hearty thanks to Microsoft team for providing this platform to organize this seminar. Expecting such a seminar once again, thank you so much to everyone.
Thank you, Deputy Gupta. Thank you. Now, it's over to Ili ma'am, Ili Pukon ma'am.
Yes, thank you. Thank you, Dipti Boravhuya and Razi Bordle. I want to thank Dr. Rishikesh Chakraborty sir and Professor Rakesh Bhet sir for making the session effective. You have selected and done some experiments through virtual lab, and I think all these will help our participants. And for the participants, thank you participants, because without you, speaker does not exist. Special thanks to Dr. Jiban Soikia, one of the participants, for making the session interactive by asking many questions. So thank you all. Now, over to Pinaki. She will wind up the session. Over to Pinaki.
Okay, I'm here. So good evening, everyone present on this platform. So today we are winding up the second day of the national workshop, that is the remote access to lab on a screen, with the objective of the familiarization of virtual lab. So on behalf of the organizing committee, I thank Dr. Rishikesh Chakraborty, Assistant Professor, Department of Physics, Jorhat Engineering College, and Professor Rakesh Bhet sir, Department of Electronics, University of Jammu, for their wonderful and effective presentation on their respective topics. To Dr. Rishikesh Chakraborty, I don't think he is present here, or I have not seen him now. But still, though the topic he has selected, optics and error analysis, but we must say that there was no error in his explanation. Am I right, Rajiv sir? Then
yes,
Professor Rakesh, to Professor Rakesh Bhet sir, we are actually not finding words to thank you, because you are associated with the whole this workshop from the very beginning wholeheartedly. So actually, we are sparing the time for the greater benefit of the students and the society as a whole. So a big thank you to you all. To Rakesh Bhet sir, a big thank you. You are associated wholeheartedly. You are associated from the starting of the inaugural session. So thank you, sir. And I thank all the participants for observing both the practice and the technical sessions so patiently and with keen interest. And thanks to the coordinator, Rajiv Bordle sir, for coordinating the session. Thank you once again all. And see you tomorrow for our next session. So thank you all. Thank you, Bhet sir, for joining us.
Thank you so much.
So we'll be happy if we see you again in our next sessions also.
Definitely.
Yeah, sir. So we will see you again, and you are there. You are collaborating institutes that you are from the collaborating association. You should be there also. So I think, yeah. Thank you, sir. Thank you all.
Thank you so much.
Okay,
Thank you.
Thank you.